This is congruence modulo an relation. Modulo n is an equivalence relation. This we have talked in our previous lecture on relations, and we have defined an example on that. Now we will give definition. So the definition is 1.3.12 is that let E be an equivalence relation. A relation is an equivalence relation if it is reflexive, symmetric, and transitive. So just to remind, relation on a set A, and for all x in A, we denote this symbol a set. Which contains all those y inside the set A such that those y are E related to x. Then this set is equivalence clause for that relation with respect to E. You can say with respect to E. Determined by x. We have a theorem. (1.3.13) let E be an equivalence relation on the set A, then 1 for all x in A, this equivalence clause is not phi, is non-entity. This equivalence clause will have some element. 2, if y is in equivalence class, then the equivalence class of x and the equivalence class of y are similar or same or equal, where x and y both are in set A. 3, for all x comma y in set A, either their equivalence class is same or equal, or the intersection between the equivalence clauses is phi. There is nothing common. And 4, if A can be written as the union of all x in A, in the equivalence clauses, in the union of all the equivalence classes for all elements in A, i.e., you can also say in words that A is the union of all equivalence classes with respect to E. We can prove this theorem. It's a very simple one, so we try to prove it. Let's try. So proof 1. 1 says that if you take any element from A, then the equivalence class with respect to that element is non-empty. And to do that, we say that, so we take an element A, since E is reflexive, so we said X is E related to X. Hence, this means there is X inside its own equivalence class, and so this equivalence class of X is non-empty. 2 says if there is Y inside the equivalence class of X, then the equivalence class of X and the equivalence class of Y both are similar or same for every X and Y inside A. So that shows that we can show by considering that Y is in the equivalence class of X, then we have by definition that Y is X related, and by symmetric property of E, X is E related to Y. In order to show that, the equivalence clause is same, we will show that we will show the contentness. We will show that equivalence class of X is a subset of equivalence class of Y, and the equivalence class of Y is also a subset of equivalence class of X. This result will follow from the theorem 1.1.1. So by theorem 1.1.1, to show two sets are equal, we show the contentness. We show these subsets. We show that each of them is a subset of each other. So this is what we show. So by theorem 1.1.1, let U be an element inside the equivalence class of Y, then U is E related to Y, or since U is E related to Y and Y is E related to X, then by transitive property, by transitivity of E, implies that U is E related to X. If this is the case, hence U is in the equivalence class of X. Thus, equivalence class of Y is a subset of equivalence class of X. Now let U is in equivalence class of X, then U is E related to X. Since U is E related to X and X is E related to Y, then U is E related to Y. Hence, this is also contained in Y. Consequently, they are similar. Sorry, they are equal. Equivalence class of X and the equivalence class of Y are equal. Now, number 3. Let X comma Y are in A. Suppose, wait. So number 3 says that if we have for every element inside A, either the equivalence classes for those elements are similar or there is no common element between them. So we are proving that by considering 2 elements inside A, and we suppose that their intersection is phi. The intersection between their equivalence class is not phi. Yes, it's not phi. Then, if that's not phi, then there exists an element in the intersection. Thus, if that element is in the intersection, that element is in both equivalence classes, okay, and this shows that it is U is E related to X and U is E related to Y. So Y is E related to X. This implies that Y is in the equivalence class of X. Hence, by 2, they have equal equivalence class. Right. Now, number 4 is A can be written, A is equal to the union of all the equivalence classes for all the elements inside A. So we can prove that by saying that let X is in A, then X is in the equivalence clause of X itself, which is contained in the union of all the equivalence classes. Thus, A is subset of this union. Also, every element of A also this union is also a subset of A. Hence, A can be written as the union of all the equivalence clauses for all the elements inside A. This is a proof of the theorem. Perfect. Now, to why we are doing this relation kind of section relations, it is very important to learn about the relations, and to learn about the relations we need to learn, after that we can learn the equivalence relations. And then if we know about the equivalence relations and then equivalence classes, then we can talk about the partitions of a set. So let me define what is a partition of a set. Let's say we have a set A and we denote a partition P be a collection of non-empty subsets of A. Then this P is called a partition of A if the following properties are satisfied. Following properties are satisfied. Again, FPRS is following properties are satisfied. Number one, for all B, C, B comma C inside this partition P, inside the collection of non-empty subsets of A, either B is equal to C or B and C have no common element. B and C have no common element. Number two, the union of all the non-empty sets inside this P is actually equals to A. What is A? A is the set for which P is a collection of non-empty sets, subsets. So P have all the non-empty subsets of A, and then if we take any two subsets of from P, and then there can be two things, like there can be one thing between them. Either both subsets are equal or there is nothing common in between them. Or, and number two property is that if we take all the subsets inside P and we union them, we combine them, we will get A. That is the definition for a partition. And We will talk about it by the example. So let's define an example. Number one, we say that we have a set which is 1, 2, 3, 4, 5, 6 elements. We say that A1 has 1, A2 has 2, 4, 6, and A3 has 5, 3, 5. Now, A is indeed a union of A1, A2, A3. A1 union A2, A3. That is the property 2 satisfied. Number one. For number one, we can say A1 intersection A2 is phi. A1 intersection A3 is also phi. And A2 intersection A3 is also phi. Hence, this P, which contains A1, A2, A3, is a partition of A. Topology for a set. You can also define a topological space for a set with some other condition, maybe. So, number two example is, we say that we have a set of integers and we relate that A be the set of all given integers, the set of even integers, and B is the set of all odd integers. Perfect. Then A intersection B is phi. Is phi, not is phi. There is nothing common between these two sets. And if you combine these two sets, you will get Z. Thus, P contains A comma B, which is a part, and is a partition of Z. Theorem. And now, what is the relation between an equivalence class and a partition? We have a theorem. So, theorem says, theorem 1.3.16 says, let E be an equivalence class or relation on the set A, then P is what? P is the collection of all the equivalence clauses such that for all the elements inside the set. And this is a partition of A. So that means that the equivalence class or the equivalence relation for set A and the partition are very related. Equivalence relation give us the equivalence classes, and the partition contains all those equivalence classes. And if we simply define that using a famous kind of example we use in group theory, ring theory, field theory. Then we have the following example, which says that this is 1.3.17, which says that let's consider a well-known famous equivalence relation. So consider the equivalence relation congruence modulo n on the set of integers as defined before, and let Zn be the partition which contains all the equivalence classes for every x in Z by theorem 1.3.16. Zn is a partition of Z. It is very clear. Now, let's say we have n6. Then we claim that Z6 have these elements, and say for iota, equivalence class for iota is 0 plus iota plus minus 6 plus iota plus minus 12 plus iota and so on. And this can be written as 6q plus iota, such that q is integer for all I. Sorry, that's not iota. That's just that's I is just an element inside Z. Perfect. Now, this shows every equivalence class 0, 1, 2, 3, 4, 5 have what kind of elements. So this shows this if the equivalence class I is a general equivalence class, and then if you take 0, then that equivalence class have elements. So if I can write the equivalence class for 0 inside the integers, that would be equals to 6, 12, 6, 12, 18, 24. Then the equivalence class 1 would include elements like 7, 13, 19, 25. And then equivalence class 2 would be like 8, 14, 20, 26. And then equivalence class 3 would be like equivalence class 3 would be like So one more thing which I want to say is this state is also equals to the following one. This is one. This is so you can see if I divide this 7 to 13, 19, 25, I'm getting the remainder 1. So these are the reminders. 0 reminder, 1 reminder, 2 reminder, 3 reminder. Okay. Similarly, when 3 reminders, simple is like this. So this is 9, 15, 21, 27, and so on. And then you can write for 4, that is 10, 16, 22, 26, 28, sorry, and so on. And then 5 is 11, 17, 23, and 29, and so on. Right? And that's how we define this equivalence class I. Now, now we have a theorem that for any partition, we can associate an equivalence relation. So let's say that in a formal way. So we have a theorem 1.3.18 says that let P be a partition of the set A. We define a relation E on A by for all x comma y inside A, where x is E related to y if there exist B in P such that x comma y is inside B. So let's say P is a partition of the set A. Define a relation E, which is an equivalence relation on A by for all x and y inside A, and we know that x is E related to y if there exists some set, some subset B inside the partition P such that these x comma y belongs are also in B, then E is an equivalence relation on A, and the equivalence classes classes are precisely the elements of P. So that's for sure. We have a partition of the set A. We can define a relation on the set A for all the elements inside A by saying that these elements are that relation related to, like they are related by that relation to each other. If there exists a subset B, if there exists B inside the partition set of all the subsets, non-empty subsets of A, so that is B, such that x comma y are contained in B. Then this E is an equivalence relation on A, and the equivalence classes are precisely the elements of the partition. So all those non-empty subsets are the equivalence classes for the set A. We can prove this, but there is not enough time and no need to. We can talk about the equivalence relation in this theorem, that the relation E in theorem 1.3.18 is called the equivalence relation on A induced by the partition. P. We know that new relations can be constructed from existing relations. So, for example, let R and S are relations on A and B. So R is a relation for A and B is a relation. S is a relation for B. Then we can have relations. We can form relations from R intersection S, R union S, R difference S, and then A cross B difference R in a natural way. And in all these relations, the domain and the range of the relation under consideration are subsets of A and B, respectively. So the domain and range of these relations are subsets of A and B. Perfect. Now, given a relation R for a set A into the set B and a relation S from a set B into the set C, there can be another relation from set A into the set C in a natural way as follows. We can also do that. We can also compose some relations to form a new relation. So let's define that by a definition. Let's let R be a relation from a set A into a set B, and S be a relation from set B into set C. The composition of R and S denoted by this sign, the relation from A into C. To C, and it can be defined by X is S compose R related to Y if there exists Z in B such that X is R related to Z and Z is S related to Y. For all X in A and Y in C. Perfect. So we can give a remark that let R be a relation on a set A, then recursively we define a relation R and we can define we define a relation N for N in N as follows. That R1 is R, Rn is the composition of R to Rn minus 1 if N is greater than 1. Then on the basis of this, we can give a definition. So the definition says that we have a relation R from a set A into a set B, the inverse of R. R denoted by inverse is the relation from B into A. Now we know these concepts by high school, by college mathematics, and something like that. And we think like, oh, I know this. But the way of writing and then the formal language for these is always important. So that's why I'm explaining these things because we should know that what kind of language we are expecting in the group theory. And this is the language we are expecting in the group theory. Okay. The following theorem gives us the necessary and sufficient condition for a binary relation to be an equivalence relation. And that is a very, very important theorem. So, and the last theorem for this lecture says that we have a relation R A, then R is an equivalence relation on A if and only if one, the symmetric order is a subset of R where the symmetric difference is a set which contains order pairs like this kind of reflexivity. 2, that R is equal to its inverse. So the relation R and the inverse relation, they are both similar. And 3, when we compose R to R, it is still a subset of R. And there we end our this lecture. Good luck. Bye.